Welcome back. In the previous session, we discussed two fundamental concepts, the range space and null space of a linear operator. Range space represents all the possible vectors that a linear operator can produce, while the null space represents its blind spot, the set of all vectors that are mapped to 0 by the operator. In this session, we move one step deeper into understanding how to decode a complex system. We will discuss eigenvectors and eigenvalues of a matrix, two concepts that reveal the inherent structure of any linear transformation. Just as a skeleton defines the structure and motion of a body, eigenvalues and eigenvectors define the internal structure and modes of behavior of a linear operator. Every dynamic pattern that operator can exhibit is compactly represented within these two ideas. Let M be a linear operator that maps Cn into itself. In this case, M can be represented as an n by n square matrix. We know that a subspace can be formed by a scaling, that is, by a stretching or contracting a vector in both directions along a line. Is there any vector that when the operator M acts on it, the outcome is simply a scaled version of the same vector? A stretched or contracted but not rotated or redirected? If such a vector exists, then every scalar multiple of it will also share this property because M is a linear operator. Therefore, this vector defines a one-dimensional invariant subspace of Cn. Even better, if we can find n linearly independent vector of this kind, they would form a basis of Cn. In this case, the representation of M in this new basis become remarkably simple. The operator would act merely by scaling each coordinate direction independently. Fortunately, vectors of this type do exist and called them eigenvectors. But unfortunately, we cannot always find n linearly independent eigenvectors. That is what leads to more complex structures such as Jordan blocks. Formally, a scalar lambda in complex field is called an eigenvalue of M if there exists a non-zero vector v in Cn such that M times v is equal lambda times v. This concept is intimately related to the range and null space we discussed earlier. For example, if we find a vector corresponding to the eigenvalue lambda equals 0, the vector lies in the null space of M. Hence, all non-zero linearly independent eigenvectors associated with eigenvalue 0 form a basis for null space. This also means that if a matrix has a null space of dimension greater than 1, there must be more than one eigenvectors associated with the eigenvalue equals 0. In order to find the eigenvalue and eigenvectors, we need to solve the equation lambda times I minus m multiplied by v equals 0. This means that v should belong to the null space of lambda times I minus m. In other words, the rank of this matrix should be less than n. So, lambda must be such that the determinants of lambda times I minus m vanish. We call this determinant the characteristic polynomial. It's a polynomial of degree n and it has exactly n roots. Each of those roots is an eigenvalue of m. Once we find the eigenvalues, finding the eigenvectors is straightforward. We just need to find the basis of null space of lambda times I minus m. Depending on the rank of this matrix, we may have anywhere from 1 to n basis vectors for null space. Eigenvalues and eigenvectors are not just abstract mathematical concepts. They are among the most powerful tools for understanding and simplifying complex systems. In control theory, they play a central role in describing how systems behave, evolve, and respond over time. One of the greatest advantages of working with eigenvalues and eigenvectors is that they allow us to diagonalize a matrix or perform what is called modal decomposition. This means we can express a complicated high order system as a set of independent modes, each governed by a single scalar value, its eigenvalue. In this form, the system becomes much easier to analyze and interpret since the coupled dynamic in the original coordinates transform into a set of decoupled equations that evolve independently. Each eigenvectors defined the direction of pattern in which the system moves when it evolves according to its corresponding eigenvalue. By looking at these eigenvectors, we can see how each state variable contributes to a particular dynamic mode. For example, in mechanical systems, eigenvectors describe mode shapes, the unique spatial patterns of the vibration or movement. In general, they reveal the internal structure of the system behavior. Finally, eigenvalues tell us everything about the stability of a linear system. By examining the location of eigenvalues in the complex plane, we can immediately determine whether a system is stable, unstable, or marginally stable. In summary, eigenvalues and eigenvectors act as a DNA of a linear system. They encode its fundamental modes, its structure, and its stability properties. Understanding them transform an otherwise complex matrix into a set of simple, interpretable components that fully describe how the system behaves. Alright, in this slide, we are going to take about a very important property of eigenvectors, their independence. We will see that when a matrix has distinct eigenvalues, the corresponding eigenvectors are automatically linearly independent. This is a powerful result because it gives us a condition under which we can form a basis entirely from eigenvectors, allow us to diagonalize the matrix corresponding to a linear operator, and greatly simplify. So let's assume our matrix M has several eigenvalues, say lambda 1, lambda 2 up to lambda n, with corresponding eigenvectors v1, v2 to vn. Here we want to show that eigenvectors that correspond to distinct eigenvalue are linearly independent. Suppose, for the sake of argument, that these eigenvectors are not independent. That would mean we could take some combination of them, say a1 times v1 plus a2 times v2, and so up to an times vn, and get the zero vectors. Next, we apply m to both sides of this equation. Because each eigenvector is scaled by its corresponding eigenvalue, we get a new equation, a1 times lambda 1 times v1 plus a2 times lambda 2 times v2, and so on. If we subtract lambda 1 times the original equation from this new one, the first term cancel out, leaving only the rest. Terms like a2 times lambda 2 minus lambda 1 times v2, and so on. Since all the eigenvalues are distinct, each of these differences, for example, lambda 2 minus lambda 1, uh, lambda 3 minus lambda 1, and so forth is non-zero. The only way the new equation can hold if all the coefficients a2, a3 up to an are 0. And when we plug that back into the first equation, I mean this equation, we also find a1 must be 0. So the only possible solution is that all coefficients vanish, which means the eigenvalues, eigenvectors are linearly independent. Cool. This is a key result. It tells us whenever a matrix has distinct eigenvalues, we are guaranteed to have a full set of independent eigenvectors. That's exactly what makes diagonalization possible, because these independent eigenvectors form a basis in which the matrix acts as a simple scaling operations on each coordinates. Now let's make this argument concrete. Suppose we use eigenvector of matrix M as a basis for a space Cn. We want to see what the representation of M looks like in this new basis. There is a change of basis matrix, let's call it Q, such that when we perform the transformation Q inverse time M times Q, we obtain a new matrix which we call that capital lambda. Our goal is to see what form this new matrix has, what form capital lambda has. We know that Q is defined by the coordinate representation of new basis with respect to the old one. That means we can construct Q by placing each eigenvector of M as a clone in Q. Now, when we multiply M by Q, the result is a matrix whose clones are simply M times V1, M times V2, and so on. But since V1, V2 to Vn are eigenvectors of M, each of those products can be replaced by its corresponding eigenvalue times the eigenvectors. So M times Vi becomes lambda I times Vi. We can factor out the eigenvectors again, which means that the transformation matrix Q inverse times M times Q become a diagonal matrix whose entries are the eigenvalues lambda 1, lambda 2, and so on along the main diagonal. Therefore, when all the eigenvalues are distinct and we use the corresponding eigenvector as a basis of Cn, the matrix M has a diagonal representation with respect to this new basis. This is what we call diagonalization, a representation in which the matrix simply scaled each coordinate axis by its eigenvalues. Okay, let's do an example together. Assume we have a simple ordinary differential equation represented in matrix form. We start by defining the characteristic polynomial which comes from the determinant of lambda times I minus m. When we solve this determinant, we find that it has two distinct roots, lambda 1 equal 5 and lambda 2 equal 2. For each eigenvalues, there is an associate eigenvectors, and we can easily define derive eigenvectors. Geometrically, you can see eigenvectors in the old coordinate axis if this 2, 1, the black one, are old coordinate axis. V1 and V2 are the new eigenvalues, and we can use them as a basis of our new coordinate system. Now, using these two eigenvectors, we can form a change of basis matrix denoted by Q. When we apply this matrix to M, we transform it into the diagonal matrix. In fact, this diagonalization is equivalent to change of variable from x to a new variable z. Define z as a q inverse x, or equivalently x equal q times z. In the new coordinate system, the dynamic with respect to the z become completely decoupled, meaning z1 and z2 evolve independently. This makes the solution extremely simple. Each model evolves as a single exponential term, one with a rate of 5 and the other with a rate of 2. So one mode grows much faster, while the other evolves more slow. When we transformed the solution back to the original coordinate x1 and x2, we can clearly see how the system appear coupled again in the space. It's actually the combination of two independent exponential behaviors. This is a beauty of diagonalization. It uncovered the hidden simplicity of the system by showing that in the right coordinate system, the dynamic are just independent exponential mode. And by watching the eigenvectors, we can see how each state define the decoupled dynamic. For example, here in Z1, the effect of state 1, x1, is twice the effect of x2. Now let's look at what happens when a system has a repeated eigenvalue, meaning some of the eigenvalue appear more than once. We start with the characteristic polynomial, which we called delta of lambda. It can be written as a product of several factors, one for each distinct eigenvalues. We say delta of lambda equals the product from I equals 1 up to s of the terms lambda minus lambda sub I raised to the power of m sub I. Here, lambda sub I is the ith eigenvalue and m sub I tell us how many times the eigenvalue is repeated. If an eigenvalue appears twice, we raise its factor to the power of 2. If it appears 3 times, to the power of 3, and so on. Since this polynomial represents n by n matrix, its total degree is n, which means that sum of all those multiplicities, m1 plus m2 to ms, must also equal n. That's just a way of saying that an n-dimensional system always exactly has n roots. Now, for each eigenvalue, two different things can happen. In good case, something very nice happens. The number of independent eigenvectors we get matches the number of times that eigenvalue is repeated in the characteristic polynomial. To understand this more deeply, I think in terms of rank and null space. When we look for eigenvectors, what we actually do is solve the equation lambda times I minus m times v equals 0. That equation defines the null space of matrix lambda times I minus m. Now, if the null space is large, meaning it has as many dimensions as multiplicity of the eigenvalue, then we have enough independent direction to build a full set of eigenvectors for that eigenvalue. In this case, the rank of the matrix lambda times I minus m drops exactly by the same number. So if the eigenvalue appear 3 times, the rank drops by 3 and the null space becomes 3-dimensional. Geometrically, this means that the matrix has 3 independent directions that is simply scales by same factor, same eigenvalue. It means we have one eigenvalue and eigenvectors scale with the same eigenvalue. Together, they span a small subspace of entire vector space, which can the eigenspace correspond to this eigenvalue. We will see when this happens, we say the matrix diagonalizable because we can find enough independent eigenvector to form a complete basis for the system. In the new coordinate system, the matrix acts like pure scaling along the each eigenvector direction. So even though one eigenvalue might appear several times, each repetition still gives us a distinct direction and everything stay nice and simple. Now let's talk about the second case. Here an eigenvalue still appear multiple times in the characteristic polynomial, but when we try to find eigenvectors, we realize we don't get as many as we should. Let's think about it again in terms of the rank and null space. When we solve the equation lambda times I minus m times v equals 0, we look at its null space, the set of all eigenvector corresponding to that lambda. In this case, the null space turns out to be smaller than expected. That means the rank of the matrix lambda times minus m hasn't dropped enough. It's higher than it should be, and therefore the null space has fewer dimension. If the eigenvalue appears 3 times, but we only find 1 or 2 independent eigenvectors in null space, that means the dimension of null space is smaller than the eigenvalue's multiplicity. We assume it as a GI, and I will define that as a geometric multiplicity. This is a problem because we cannot form a complete basis for the system just using the ordinary eigenvectors. We are missing some directions. Geometrically, it's as if several axes that should have been independent have no collapse into each other. The matrix is still acting like it has that repeated eigenvalue, but we don't have enough unique directions in space to fully separate those modes. As a result, the matrix can no longer be diagonalizable. There aren't enough independent eigenvectors to make that possible. So to fix this, we need to include new kind of vector, not true eigenvectors, but related ones that complete the structure. We call them generalized eigenvectors. They are specified, they are specially constructed to fill in those missing direction and to restore a full basis for the system. Today, we will see how these generalized eigenvectors are found, how they like together to form what we call Jordan chain, and how this leads to the Jordan canonical form, which gives us a complete understanding of the system even when diagonalization fails. Based on what we have just seen, when we try to find eigenvectors for a particular eigenvalue, two important quantities naturally appears. We call them algebraic multiplicity and geometric multiplicity. Algebraic multiplicity tell us how many times a specific eigenvalue appears as a root of the characteristic polynomial. So if the eigenvalue lambda I shows up twice, its algebraic multiplicity is 2. If it appears 3 times, the algebraic multiplicity is 3, and so on. We usually denote this number as m sub I, and the geometric multiplicity tell us how many independent eigenvectors we can actually find for that eigenvalues. It's the dimension of null space of the matrix lambda I times I minus m. We usually call this number GI. The relation between these two multiplicities determines whether or not the matrix can be diagonalizable. If for every eigenvalues the geometric multiplicity and algebraic multiplicity are equal, then the matrix is diagonalizable. This means the null space gives us exactly as many independent eigenvector as the eigenvalues multiplicity, no more and no less, and that's exactly what happens in a simple case of distinct eigenvalue. Each eigenvalues appears only once, so the algebraic multiplicity is 1, and the dimension of null space is also 1. They match perfectly and diagonalization works beautifully. But now we see that this is actually just a special case of a more general rule. In general case, if for every eigenvalue the algebraic and geometric multiplicity are equal, then the matrix can still be diagonalized even if some eigenvalue repeated. However, if for at least one eigenvalue the geometric multiplicity is smaller than the algebraic multiplicity, diagonalization becomes impossible. In that case, we cannot make the matrix fully diagonal, but we can still transform it into a special form that looks almost diagonal. That special form is called Jordan form, and it's what we will discuss today. Let's now see how the previous theorem actually works in practice. Throughout a very simple example, here we have a matrix, let's call it M. The characteristic polynomial of this matrix is lambda minus 2 times lambda minus 1 square. So it's easy to see that this system have two eigenvalues. One of them is lambda equals 1, which has a multiplicity of 2, and the other is lambda equal 2, which has a multiplicity of 1. Let's start by exploring the null space associated with lambda equals 1, the repeated eigenvalue. To do that, we look at the matrix lambda times I minus m when lambda equal 1, and we compute its rank. When we check that, we find that the rank of this matrix is 1. From the rank nullity theorem, we know that the dimension of the null space is equal to the total number of columns minus the rank. Since the matrix is 3 by 3, that means the null space has dimension 2. That is the case we really like because the algebraic multiplicity and geometric multiplicity are equal. In the other word, we have repeated eigenvalues with two independent eigenvectors. So this matrix is diagonalizable with respect to that eigenvalue. Next, let's look more closely at the structure of the null space. When we solve the equation lambda times I minus m times v equals 0 for lambda equal 1, we find that the third component of the vector, let's call it v3, must be 0. That means all the eigenvectors correspond to this eigenvalue lies on the xy plane in three-dimensional space. Assume we have a three-dimensional space and all the the eigenvectors correspond to this eigenvalue lies on the xy plane. So we can choose two simple basic vectors to represent this null space. For example, we choose standard vectors, v1 as a 1, 0, 0 and v2 as a 0, 1, 0. These two vectors are independent and together they span the null space for lambda equal 1. Now let's move to the second eigenvalues, lambda equal 2. We do the same thing. We form lambda times I minus m for lambda equal 2 and find the null space. When we solve that equation, we find that the null space satisfies v2 equals 0 and v1 equal negative v3. So in this case, the eigenvector lies a line where x equal negative z and y equals 0. If we visualize all of this, we can imagine the original coordinate system as x, y, z axis and the new coordinate system formed by the eigenvectors as a set of red dashed vectors. Notice that v1 and v2 correspond to the first eigenvalue are orthogonal to each other, but the third one, v3, which comes from the second eigenvalue, is not orthogonal to them. Still, if we redefine our linear operator m in the new coordinate system, that is, if we express the system with respect to this eigenvector direction, or we define delta equal q inverse m times q, the matrix representation of m become diagonal or equivalently act as an orthogonal transmission along this new direction. This example perfectly illustrates idea of algebraic and geometric multiplicity and show how diagonalization works. These two multiplicity are equal. Let's take a moment to review what we have done so far. Our goal has been to find a coordinate system in which the matrix acts as something very simple, a pure scaling along independent direction. In the spatial coordinate system, each axis corresponds to an eigenvectors and the scaling factor along that axis is eigenvalue. To make this happen for every eigenvalue, we need a certain number of independent directions. Directions along which the matrix entries scratch or compress the space. The algebraic multiplicity tells us how many times a particular eigenvalue appears as a root of the characteristic polynomial, and the geometric multiplicity tells us how many independent directions we actually have for the eigenvalue. That is, how many independent eigenvectors exist in the null space of lambda times I minus m. When these two numbers, algebraic multiplicity and geometric multiplicity, are equal, everything works beautifully. We have just enough independent eigenvector to span the entire n-dimensional space, and the matrix can fully diagonalize. But the real challenge begins when the algebraic multiplicity is greater than geometric multiplicity. That means we don't have enough independent vectors to cover all the direction we need. In other words, we are missing some dimension in our coordinate system. So from this point on, our goal is to understand how to fix this problem, how to find additional vectors that can fill in the missing direction, and how to represent the matrix in a form that still captures its full behavior even when diagonalization is not possible. That leads us naturally to the concept of generalized eigenvectors and the Jordan canonical form, a powerful framework that shows how every linear system can still be decomposed into simple structure parts. Now let's see what we can do when we don't have enough eigenvectors, when the geometric multiplicity is smaller than the algebraic multiplicity. We cannot diagonalize the matrix in the usual way. So to add more vectors and complete our basis, we introduce a new concept, the generalized eigenvector. A vector is called generalized eigenvector of grade k if when we multiply it by the matrix lambda I times I minus m raised to the k's power, we get 0, but when we multiply it by 1 power less, that is the k minus 1's power, we don't get 0. In other words, this vector lives in the null space of k's power of lambda I times I minus m, but this is not belong to the null space of the k minus 1's power. That's why we called it generalized eigenvector. It's not a true eigenvector, but it's closely related to 1. Now, once we find such a vector, we can build what we called a chain of generalized vectors. For simplicity, let's look at an example. Suppose k equal 4. We have a generalized eigenvector of grade 4. Let's call it v4. From this vector, we can construct 3 more vectors as follows. We define v3 as a lambda I times I minus m times v4, or equivalently v, and v2 as a lambda I times I minus m times v3, and v1 as a lambda I times I minus m times v2. If we track this chain, we can see that lambda I times I minus m applied to v1 gives 0. That's because v4 was in the null space of the 4th power, because v4 is equal v and v is a generalized eigenvector. So when we apply the operator 4 times goes 0, but the earlier vector in the chain are not 0. That's what makes the chain meaningful. Now something interesting happened when we look at how the matrix M acts on this vector. If we multiply M by v1, we get lambda times v1. That's the usual eigenvector. If we multiply M by v2, we get lambda times v2 plus v1. For v3, it becomes lambda times v3 plus v2. And for v4, it becomes lambda times v4 plus v3. So every time we move one step up the chain, the result depends on both the vector itself and the one just below it. This structure naturally leads us to something called Jordan block. If we take all these vectors, v1, v2, and v4, and arrange them as the clone of a matrix, then multiply that by m, we find m acts on them throughout a special kind of square matrix. This new matrix looks almost diagonal. It has lambdas along the main diagonal, ones just above the main diagonal. See, one just above the main diagonal and lambda align the main diagonal. We call this matrix as a Jordan block. For this case, since we have 4 vector in the chain, it's 4 by 4 Jordan block. In general, for a generalized eigenvector of grade k, the corresponding Jordan block is a k by k matrix, and we denote it as a j sub k of the lambda. It means that even if a matrix doesn't have enough ordinary eigenvectors, we can still construct a complete basis using generalized eigenvector. And when we represent the matrix with respect to that new basis, it takes on a block diagonal form made up of these Jordan blocks. This form is not purely diagonal, but it's diagonal-like, and it captures exactly how the matrix stretches and mixes directions when there aren't enough independent eigenvectors. It's one of the most powerful idea in linear algebra and is the foundation of Jordan canonical form. But there is another important point we should emphasize here. In every Jordan chain, the first vector, v1, is actually a true eigenvector of the system corresponding to eigenvalue lambda. So if the null space corresponding to a particular eigenvalue lambda has a geometric multiplicity of gi, it means we have gi linearly independent true eigenvectors for that eigenvalue. Each of these eigenvectors can then be extended or generalized into a chain of higher grade generalized eigenvectors. We have gi true eigenvectors, so we can generate gi chain of generalized eigenvector. For each real eigenvectors, we can build a sequence of vectors connected by the operator lambda times I minus m. Each step in the chain represents applying the operator one more time, and at the end of the chain, the operator finally sends the last vector to 0. But now a very natural question appears. We have gi eigenvectors correspond to each eigenvector. We have a chain, but the question is that how long can each of these chains be? Or in the other word, for a given eigenvector, how many generalized vectors can be attached to it? What determines the grade of the generalized vectors chain correspond to a special eigenvectors? This is a key question. How far we can go in building a chain. Now let's finally discuss how to find generalized eigenvectors, and more importantly, how to determine how far we can extend each chain. We start with an eigenvalue, let's call it lambda I, which has an algebraic multiplicity of mi and a geometric multiplicity of gi. This means that the null space of lambda I times I minus m has a dimension of gi. So we have gi independent eigenvectors to begin with. As we discussed before, for each eigenvector, we can form a Jordan block, but we still don't know the size of each block. In other words, we don't yet know how many generalized eigenvectors belong to that chain. So how can we define this? Let's think about the process step by step. We start from the basic matrix, lambda I times I minus m. First, we look at the null space that gives us the true eigenvector. Then we square matrix and check the null space again. Then we take the cube and so on. Each time we raise the power by 1 and look at how the null space grows. matrix, we will see that the dimension of null space grows. And here is the key fact. The null space of a lower power is always contained inside the null space of a higher power. That's because when we multiply the matrix by itself again, we lose more information, or in a geometric term, we filter out more directions. You can think of a matrix as a kind of filter. Every time you apply it to a vector space, it removes some component or collapse some directions. If you apply it twice, you lose even more. So as we go to the higher power, the rank of the matrix decreases. And by the rank nullity theorem, when the rank decreases, the nullity, that is the dimension of the null space, must increase. This gives us a simple but powerful insight. Each time the dimension of the null space increases, a new generalized eigenvector has been created. So here's what we do. We start from the null space of lambda I times I minus m. Then we compute the null space of its square, its cube, and so on. We track the dimension of each null space at every step. Let's call dimension S1, S2, S3, and so on. Then we define delta I at each step as the difference between two consecutive dimensions. For example, delta 2 equals S2 minus S1. Whenever this difference increases, that tells us a new generalized eigenvector has appeared. We continue this process until the dimension of the null space equal the algebraic multiplicity mi. After that moment, we have found all the vectors, both the regular eigenvectors and generalized ones, that we need to form a complete basis for eigenvalue. So the smallest power k, for which the null space of lambda I times I minus m to the k's power has dimension mi, give us the maximum grade of the generalized eigenvector for that eigenvalue. From this step, we can form all the Jordan chain of the length up to k. If we need more vectors, meaning we still had not reached the total multiplicity, that would tell us this k is too small and we would move to the next higher power. So delta of k tell us how many chain extend to that length or beyond. And tracking the delta give us a direct way to understand the structure of the Jordan form. Alright, now we have this intuition. Let's continue our investigation with a simple example to see how this delta value appear in practice and how they reveal the exact shape and size of a Jordan block. Okay, let's now see what happens when we actually try to diagonalize, or if that's not possible, to derive the canonical Jordan form of a special matrix. The first step, as always, is to find the characteristic polynomial of the matrix. In this case, the characteristic polynomial has two factors. One is simply lambda, and the other is 2 minus lambda raised to the 5th power. So this matrix has two distinct eigenvalues. The first one, lambda 1 equal 2, and the second one, lambda 2 equal 0. The eigenvalue 2 has algebraic multiplicity of 5, and the eigenvalue 0 has an algebraic multiplicity of 1. Let's focus on the eigenvalue 2, since that's the one with the higher multiplicity. That's where things get interesting. Two general situations can occur here. First case, if the null space corresponding to lambda 2 has dimension 5, that means we can find 5 independent eigenvectors. And because the algebraic multiplicity is also 5, this satisfies our diagonalization condition. So the matrix is diagonalizable. In that case, the Jordan form is simply a diagonal matrix with the eigenvalue 2 repeated 5 times along the diagonal, plus one more entry from lambda equals 0 in the bottom right corner. In the second case, if the null space corresponds to lambda equal 2 has dimension less than 5, then the matrix is not diagonalizable, and we will instead have one or more Jordan block associated with that eigenvalues. Let's go through the possible one by one. If the dimension of the null space or geometric multiplicity is 1, that means there is only one independent eigenvector for lambda equal 2. So all 5 algebraic dimension must be represented by a single chain that give us one Jordan block of size 5 by 5. If the geometric multiplicity is 2, that means there are 2 independent eigenvectors and therefore 2 Jordan blocks. But we have to decide how those 5 dimensions are distributed between them. We could have one block of size 4 and another of size 1, or we have one block of size 3 and another of size 2. Both satisfy the total size of 5, but they represent different Jordan structure. If the geometric multiplicity is 3, again, 2 different patterns are possible. And if the geometric multiplicity is 4, then only one configuration is possible. One block of size 2 and 3 block of size 1. In general, the number of Jordan block associated with a given eigenvalue is equal to geometric multiplicity, because each independent eigenvector starts one chain. So if the geometric multiplicity is 2, there are exactly 2 chains and therefore 2 Jordan blocks. However, to know which specific configuration occur, for example, whether the size are 4 and 1 or 3 and 2, we need to look deeper into how the null space dimension change as we increase the power of lambda times I minus m. That's where the delta k value we discussed earlier become crucial. By observing how much the null space grows at each power, we can precisely determine how long each Jordan chain is, and therefore how large each Jordan block should be. Now let's see what happens when we start increase the power of the m minus 2 times I. You might be noticed that sometimes we write it as a lambda I minus m and sometimes as a m minus lambda I. Theoretically, there is no difference between these two forms. They have exactly the same null space, the same range space, and the same eigenvalues and eigenvectors. So switching between them doesn't change any of our conclusion. Let's now analyze what happened to the range space and the null space as we increase the power of m minus 2i step by step. When we look at m minus 2i, we can see that some of its columns are linearly dependent. Column 1 and column 2 are dependent, and so are column 3 and column 4. However, column 6 and column 7 are independent. Although we find 4 linearly independent columns, which means the rank of this matrix is 4. By the rank nullity theorem, since the matrix is 6 by 6, the dimension of its null space, let's call it S1, is n minus 4, which in this case gives us S1 equal 2. So the null space has dimension 2. That means the geometric multiplicity Gi is 2. Therefore, there are 2 linearly independent eigenvectors and consequently 2 Jordan chain or 2 Jordan blocks corresponding to lambda equal 2. Now that we know there are 2 blocks, the only remaining question is how large they are. 2 blocks could be arranged as 1 block of size 4 and 1 size 1, or as 1 block of size 3 and 1 of size 2. We'll figure that out by going to higher power. When we compute this, we observe that the first and second column are now completely 0, and the third and fourth are linearly dependent. Column 5 and 6 are also dependent. So among all columns, we only have 2 independent ones. That means the rank of m minus 2 times I square is 2. Again, by the rank nullity theorem, the dimension of the null space is S2 equal n minus 2 is equal 4. So the null space groups from 2 to 4, which means that increase delta 2 is 2, and that tell us 2 new generalized eigenvectors have appeared at this stage. Since n1, the first null space, is a subspace of n2, the second one, it means that both of the original eigenvector as belong to n2. In other words, both eigenvector extend one step further. So each of them has at least a chain of length 2. n1 is subspace of n2, so every eigenvector that exists in n1 are in n. It means both eigenvector can generalize one step further. Now let's increase the power once more and look at m minus 2 times I to the power of 3. This time almost all column are 0 except for column 5 and 6, and even those are linearly dependent. So we have only one linearly independent column, which means that rank is 1. Therefore the null space has dimension S3 equals 5. Notice that just happened. The null space dimension increased from 4 to 5. So delta 3 equals 1. That means only one new generalized eigenvector was created at this level. And remember, the null space of second power is contained in null space of the third power. So the two eigenvector and their first level generalized are already inside N3. But now there is one additional vector that lies in N3 but not in N2. That means one of the Jordan chains contains two length 3, while the other chain stops at length 2. See, at the third level, we have one more generalized eigenvector. And we know both extended length 2, and here we know one chain extend further or equal length 3. It means we have two blocks with degree of width size of 2 and another with size of 3. So by observing how the null space grows as we increase the power of m minus 2 times I, we can identify both the number of Jordan chains, which equals the geometric multiplicity, and the length of each chain. See how the rank nullity relationship and step-by-step growth of the null space reveals exactly how to construct the Jordan canonical form. No, just the number of blocks, but their exact sizes. Now let's see how we can actually define the generalized eigenvectors for this example. We start from the highest power we used in our previous analysis. From before, we found that delta 3 equals 3 and that the null space of the second power n2 is a subspace of the null space of the third power and 3. This tells us that there must exist at least one vector that belongs to n3 but not to n2. That is an important observation because any vectors that lies in n3 but not in n2 is by definition a generalized eigenvector of grade 3. So we just need to find one such vector. It's easy to verify that the vector v equals 0, 0, 1, 0, 0 and 0 satisfy this condition. It belongs to the null space of m minus 2 times I to the power of 3, but it's not belong to the null space of m minus 2 times I to the power of 2. This will be our starting vector for generalized chain. Now that we have this top level vector, let's call it v3. We can build the rest of the chain by moving downward step by step. First, we compute v2 equal m minus 2 times I multiply v3. The second compute v1 equal m minus 2 times I times v2 by constructions v1, v2 and v3 together for a Jordan chain of length 3. The vector v1 is true eigenvector of the system correspond to lambda equal 2, and v2 and v3 are the first and second generalized eigenvector linked to it. This gives us a Jordan block of size 3 for this eigenvalue. Let's find the second chain. From our earlier analysis, we know that the null space of the second power n2 contains two vectors that are not in the first null space and one, that means there are two possible direction in N2 that could start a new generalized chain, but we only need one of them since we already have one chain combining from the previous step. Let's call this vector u. So u is an element of the null space of m minus 2 lambda times I square, but not an element of the null space of m minus lambda I. And of course u must also be linearly independent of all the vectors we already have, v1, v2 and v3. It's easy to verify that the vector u equals 0, 0, 1, minus 1, 1, 1 satisfy all these conditions. It lies in the null space of the second power. It's not in the null space of the first power. Call this vector u2 since it's the top vector in the Jordan chain of length 2. To build the rest of the chain, we compute u1 as a m minus lambda I times u2. This gives us the lower vector in the chain. We already have 5 linearly independent vectors, 3 from the first Jordan chain, v1, v2 and v3, and 2 from the second chain, u1 and u2. Since our system is 6-dimensional, we need just one more linearly independent vector. For that, we look at the other eigenvalue, which is lambda equals 0, to find its eigenvector. We simply compute the null space of M. When we do this, we find a vector that satisfies the condition m times w equals 0. We can choose the vector w equals 0, 0, 0, 1, minus 1, 0. Now we have all 6 linearly independent vectors, u1, u2, v1, v2, v3, u1, u2, and w. Let's collect them as a clone of a single matrix Q. This matrix Q serves as our change of basis or transformation matrix. When we apply this to the M converts into a new matrix that is almost diagonal, known as a Jordan canonical form. And we can see this Jordan matrix has 2 Jordan blocks correspond to eigenvalue equal to one size of 3 and one size of 2, and one additional single entry, 0 on diagonal, corresponding to eigenvalue lambda equals 0. We started with characteristic polynomial, analyze the groups of the null space, constructed all generalized eigenvectors step by step, and finally assemble transformation matrix that reveals the true model structure of M. Thank you.